Vanakkam. Welcome to this video on biomechanics. We have been looking at some practical applications. Specifically, we are interested in measuring kinematics of rigid body segments in the body, in the human body. How to measure, what are the techniques that are available, what are the methods, what are the algorithms that are available. This is of interest for us. In this video, we focus our attention on how do we parameterize rotation, what are rotation matrices, and what are rotation matrices in 2D, what are rotation matrices in 3D, some important or crucial properties of rotation matrices that help us analyze this kind of data with some ease, and visualization. Rotations are usually represented in one of these three forms in biomechanics. Common textbooks on biomechanics usually discuss rotation matrices and Euler angles. Also discuss how to convert Euler angles to rotation matrices and vice versa. Yes. Quaternions are reserved for a later chapter, usually in textbooks on biomechanics. Slowly, this topic of quaternions is gaining more and more attention with the advent of technological systems that exploit the quaternions or the specific properties of quaternions for measuring kinematics. We discussed that in this video and in the next few videos, wherever this comes. Okay. So, many systems offer a choice of in which method you want to output your data. That is, are you interested in getting this as rotation matrices or as quaternions or as Euler angles? How do you make this choice? How do you know which one is which? The first factor is whether you have a physical sense of the movement that is being performed, or can you understand, ease of understanding or visualization, because it turns out not all of them are easy to visualize. That does not mean only those that are easy to visualize are necessarily the best methods. Okay. So, these are two different things. Obviously, we are keen on understanding, we can understand and interpret and visualize angles better than something like quaternions. That does not mean that angles are necessarily the best method, because we will see what are the advantages and disadvantages for each of this as we go forward. Okay. One is that ease of understanding, ease of visualization. The other is the specific range of motion that is involved in your application. What are the expected joint angles? How much do you expect the participant or the experimental subject to move? Because if it is not going to cause any gimbal locks or singularities, maybe some methods have a distinct advantage over others. So, you need to have an idea of the range of motion that your subject of interest is going to perform, or the particular joints of interest are going to go through. The other is, are there going to be some discontinuity or continuity of data? Are there going to be some discontinuity in data? That is the other point. The other is, what is going to be the size of the data? How much or how many different markers are you measuring, or how many different particular sensors from which you are measuring? Because if it is small, then maybe your computer or microcontroller or some system can take that load, because if it becomes very large, the system cannot take that load. So, there are constraints in communication and computing technology that might come into play. Usually this is not there, but sometimes in some extreme situation this might become difficult to handle. Okay. Most importantly, you need to have an idea of the specific application that you are looking at. What is the problem that you are working on? What is the application? What is the specific problem that you are interested in? Let us say that you are interested in measuring joint angle between say the upper arm, this is the upper arm or the humerus bone, this is the forearm. What is the bone or what are the bones in the forearm? Remember, radius and ulna. Of course, I am not going to place the sensors on the bone, I am placing it on the skin. That is a different topic, that is a huge topic in itself. How do you know that if you are measuring from the skin, that is the movement, that is the motion that your underlying rigid body, the bone is undergoing? You actually do not know that. There is a whole field called STA, soft tissue artifact. There is a whole field of study and research called how soft tissue artifacts happen in kinematic measurement in humans and how to address them, how to overcome. There are ways of calibrating this and all. So, again, it all comes down to the level of accuracy that you want and the level of accuracy that is acceptable to you. Right? If you are looking at an extreme level of accuracy that you want, then you may have to account for soft tissue artifacts also. There might be movement of the sensor that might not be purely due to movement of the underlying bone because of skin deformation, because of the underlying soft tissue deformation and so on and so forth. And this will change depending on the specific range in which you are operating. At specific joint angles this will not be high, at different joint angles this will become high. Something to keep in mind. But mostly let us assume that this is not a problem that we are working with. We will assume that when I put a sensor or a marker on the skin, I assume that it is going to reflect the underlying rigid body kinematics. This is not true, I am making that assumption. So, in other words, for me, for the rest of the analysis, for me soft tissue artifact is almost not there. This is not true, I am making that assumption, otherwise we cannot proceed with the discussion. Okay. Let us say I am keeping a sensor here, I am going to call that as sensor S1 and this one as sensor S2, and I am measuring these two data. For example, in the method that we use in our lab, these two data sets will come from actually these have their own microcontrollers. Both of these report to another master microcontroller that then wirelessly communicates to a computer, which will display some movements, some data patterns or some 3D geometrical movements, right, that are generated in near real time. So, the data that is received by the PC can be either in the form of rotation matrices or quaternions or Euler angles. The specific method, the exact method that is used depends on the application. It could be any of these. We start our discussion with rotation matrices. So, rotation matrices or rotation matrix is a matrix that has or that is composed of 3 vectors that are orthogonal to each other, and each of these 3 vectors is having unit magnitude or they are unit vectors. So, essentially these are going to form a basis of an orthonormal system. Okay, these are orthonormal. Yes. And I am interested in describing rotation that a specific body, a point undergoes. Right. How do I describe that? So, for example, this is the rotation that this particular body is undergoing, that body is undergoing that rotation, right. Now, as this body is rotating, the set of vectors that are spanning this body are also rotating, is it not? Like this. So, like this as we see. Here again, I am rotating with respect to a particular axis. So, you are not seeing rotation in 3D. Actually, this is not the case in real life. The rotation can happen in 3D or about an axis that has projections onto all the three axes of interest. So, you will not see it so trivial in real life. So, but still you need to start somewhere, you need to start with the simple case. Here you have, say for example, a rotation matrix with these orthonormal vectors 1 0 0 0 1 0 0 0 1, right. So, each of these vectors represent, for example, this is the moment, this is the vector that is representing the motion in the x axis, the correspondingly in the y axis and the z axis, right. This is the identity matrix that is describing no particular rotation, no rotation is happening. Now, in this particular case, for this particular matrix, but if there is some rotation that is happening, how do we describe that? That is the question. We start with a simple case. Okay. Let us say that there is a point P here that is shown this, and initially it is having an angle of theta with respect to the horizontal axis, which is the x axis. This is rotation matrix in 2D. Okay. So, I can find out the projection of this point P onto the x axis. I am going to call that as some Px, and onto the y axis I am going to call that as some Py. And I know initially what is the angle that P itself is having, and then I am saying that this P is making a rotation about the z axis in the xy plane. In the xy plane, it is making a rotation of some known angle theta. I know the angle by which it is rotating, that angle is theta, I know this angle. The question is, what is the problem of interest for us? The problem of interest for us is, find the coordinates of the point P dash, the new point P, that is the question. Given that I know the coordinates of the point, the original point P, and the amount of rotation that has happened theta, can you tell me what is the coordinate of the new point P or P dash or P dash x, that is the x coordinate, and P dash y coordinate, what are these? That is the question. What is the coordinates of the point P dash? That is the question. Well, there are many ways of doing this, but the best way to learn is to start from the first principles. So, here we will derive the coordinates of this point P dash using first principles, and then we will define what the rotation matrix is. So, there is some intuitive understanding of what this means. Okay. I can write the value of Px in terms of P and theta. What would that be? Because Px is forming the adjacent side for theta naught, Px is forming the adjacent side of this right triangle, is it not? I am going to call this point as A and that point as B, for example. In the right triangle OAB, OA is Px, is it not? That is the adjacent side. The question is, what is its value? Well, that is because I know the length of the vector to be r, that is actually r cos theta naught. Okay. What is the value of Py? Py is r, likewise r sin theta naught, because that is Py, this is also Py, is it not? If this is Py, this is also Py. In OAP, that is forming in the right triangle OAP, that is the opposite side. There are many ways of discussing this, I am discussing in this way. Okay. So, Py is r sin theta naught. Remember that this is the case of pure rotation, in which the object is not linearly making any movement or is not undergoing any translation. So, r remains the same. In both these cases, between P and P dash, r remains the same, okay, something to keep in mind. Now, can I describe the location of P dash in the same way as I just now described P? Like I wrote for Px and Py, can I write the values of Px dash and Py dash, because that is not having the same angle theta naught, it is having an angle of theta naught plus theta, because it has undergone a pure rotation. Remember, r remains the same, the r is the same, okay. So, I write Px dash, what would that be? Well, same, right, that would be, this is a different formulation, that is actually Px dash, that is r cos theta naught plus theta, is it not? R cos, by the same logic, because this is forming the adjacent side of the right triangle, this will be r cos theta naught plus theta, because there is one more theta, because the rotation has happened by a value of theta. Py dash likewise is r sin theta naught plus theta. I can, using trigonometric identities, I can expand these two equations. I am going to call this as some, okay, let's name all of them. I am going to call this as 1, I am going to call this as 2, I am going to call this as 3, and I am going to call this as 4. Expand 3 and 4 using trigonometric identities. Using trig, I am saying trig, essentially trigonometric identities, because you know what is cos a plus b, what is sin a plus b, you know those things. That is actually Px dash, that will give me Px dash as r times cos of theta naught plus theta is actually cos theta naught minus sin theta naught, and Py dash is r times sin of a plus b, is it not? That would be sin theta cos theta naught plus cos theta sin theta naught, is it not? How do I know this? How do we know this? Trigonometric identities, right? Of course. These are trigonometric identities. We know this from high school. It's assumed. Okay. Check this though. Check this. If you are feeling absolutely unfamiliar with this, the time has come for me to pause the video. Go back and check these trigonometric identities from your high school math books. Okay. Now I can substitute the data from 1 and 2 in 5 and 6, because wherever r cos theta naught comes, I can say that is Px, and wherever r sin theta naught comes, I can say it is Py. I can say that because r sin theta naught is Py, r cos theta naught is Px. How do I know that? That is the original description. I know this. Okay. So that would give me Px dash as r times cos theta by Px by r, because I am going to replace that by this logic, cos theta naught is Px by r, and sin theta naught from 1 and 2, this is what I learned, sin theta naught is Py by r. So, I am going to replace cos theta naught as Px by r and sin theta naught is Py by r. Okay. So, that gives me it is minus sin theta naught is Py by r. Okay. Likewise, Py dash is r times sin theta cos theta naught is Px by r, okay, plus cos theta sin theta naught is Py by r. Is it not? I am cancelling r and simplifying this a little bit. After some algebra, this actually becomes, what does this become? This becomes Px cos theta minus Py sin theta, and this becomes Px sin theta plus Py cos theta Py. Now, let us write out what we got for Px dash as, what did we get? Px dash is Px cos theta minus Py sin theta, that is Px cos theta minus Py sin theta. Py dash is Px sin theta plus Px sin theta plus Py cos theta. Px sin theta plus Py cos theta. Now, I can write this in matrix form and I can combine these two equations as vectors and matrix as follows. This is Px dash Py dash, the vector is a 2 by 2 matrix, which is essentially cos theta minus sin theta and cos theta times the original coordinates Px, Py. This is the formulation of rotation matrix for this situation when the rotation happens by an angle theta in 2D, right. So, to find the coordinates in the new frame, I need to just multiply it by the rotation matrix, which is this. This is the rotation matrix. It has some interesting properties that we can exploit to simplify much of our analysis. This is in 2D. What does this imply? What is the meaning of this rotation matrix? What is the physical meaning? There must be some physical meaning for this, right? What does this do? This is the matrix, this rotation matrix is the matrix that rotates a point P whose coordinates are Px and Py by an angle theta to the new coordinates Px dash and Py dash by an angle theta. So, this is the matrix that rotates this point by an angle theta. Remember, this is in 2D. We can also have this in 3D. Would that be a trivial extension of the 2D? I will leave that as an exercise for you. Actually, in 3D, I can define these rotations as 3 rotations, Rx about the x axis, Ry happening about the y axis, and Rz, the rotation z happening about the z axis, each having its own rotations. If all of them are having the same angle of rotation, by the way, that is not a compulsion. You do not have to rotate by the same angle about all the 3 axes. That is not necessary. You could, for example, have theta, psi and some phi. You could have 3 different angles, theta, psi and some phi. In this case, it is assumed that all of them are rotating by the same angle theta. Then Rx is, because the rotation is happening about the x axis and x axis itself is not moving, right, because the rotation is happening about the x axis. Then the rotation matrix would be this. And because I know, let us say for example, I say theta is equal to 60 degrees, because I know cos theta, sin theta for value of theta 60 degrees, I can actually write out this rotation matrix, right, that value. If you rotate about the x axis, because the rotation is not going to affect the x itself, because rotation is happening about the x axis. 1 0 0, this vector will remain the same, but what was earlier 0 1 0 will rotate by 60 degrees and will become these, that is that. And z that was earlier here along the dotted line has moved to this point, whose coordinates are 0, minus 0.866 and this, right, that is there. So, these coordinates have changed. By the way, I have assumed that the rotation is happening about the x axis and the coordinates along the about the x axis are x coordinates are not changing is the assumption, but actually in this case 3D rotations can involve rotation that is happening with different angles about the 3 different axes, something that we will see in future slides. It turns out that rotation matrices have some very interesting properties, right. We mentioned this in the first one of the early slides on rotation matrix itself, that the columns of the rotation matrix are unit vectors, that they are essentially orthonormal, they form orthonormal bases. So, these are unit vectors. Also columns of the rotation matrix are orthogonal to each other, also something that we defined. Importantly, very importantly, rotation matrices are not commutative, that is matrix multiplication depends a lot on the order of multiplication. This becomes crucial in some of our discussion in future. We will discuss this in much greater detail in future. So, the order of multiplication, the order of rotation matters. Okay. Also, the inverse of a rotation matrix is its transpose, a very useful property. Okay. Now, let us say that we have this square whose coordinates are defined by these points as shown. Actually, we are having only 2 coordinates, just the x coordinate and y coordinate, where the point 1 is minus 5 comma 5, sorry, minus 5 comma minus 5, point 2 is 5 comma minus 5, point 3 is 5 comma 5 and point 4 is minus 5 comma plus 5. Okay. Now, I have this square and I am rotating this whole square by some angle, okay, by an angle of say 60 degrees. The question is, what is going to be the coordinates of these 4 points in the new rotated frame? That is the question. What is going to be the coordinates of P1, P2, P3 and P4 in the new frame? The whole square I am rotating, what is going to be P1 dash, P2 dash, P3 dash and P4 dash? That is the question. Okay. Now, I can take each of this point as a vector of a matrix, as a column of a matrix. Each of this is a vector and I can assume that they form columns of a matrix. The rotation matrix of interest for me is, because the rotation is happening about the z axis, there is going to be cos theta minus sin theta 0, sin theta cos theta 0 and 0 0 1. How do I know this? Because this is the rotation matrix of interest. The rotation is happening about the z axis. Okay. So, that is going to have 0 0 1 in the last column and 0 0 1 in the last row, and cos theta minus sin theta cos theta is going to come as the other elements of this matrix. How do I say this without much practice? I am not saying this without much practice, I am saying this because we have done a lot of this. I have done a lot of this. You will also be in a position to say this after some practice. I also just look at the matrix and I know that the rotation is happening about the z axis. How do I know? Because 1 is appearing at the point 3 comma 3 in the matrix. So, I know that the rotation is happening about the z axis. This is how you know. You know this after some practice. This is not rocket science. This is a straightforward simple principle. Okay. So, theta here is 60 degrees and I am substituting for theta here. So, I am interested in finding the new points. So, the method is the new point coordinate is essentially r times rotation matrix times the point, the vector p, and that would be minus 5 comma minus 5 for point 1, 5 comma minus 5 for point 2, 5 comma 5 for point 3 and minus 5 comma 5 for point 4. But then I have minus 5 comma minus 5 comma 0 because I am using 3D notations. Once you measure this, you realize that the points have moved to 1.83 comma minus 6.83 and 6.83 comma 1.83, minus 1.83 comma 6.83 and minus 6.83 comma minus 1.83. Remember, the square itself is not squished or elongated, right? The square is just rotated. It is not translating, it is not squished or elongated. It has undergone a pure rotation about the z axis by an angle of 60 degrees. Okay. This is a simple example. We will see more examples of this in future videos. Okay. So, in this video we looked at various ways in which we can parameterize rotation, and we saw how to derive the expression for rotation matrix in 2D, and we did not do this derivation for 3D. I will leave that as an exercise for you to do, and we discussed some of the important or crucial properties of rotation matrices that we will take advantage of while solving problems. And we saw some example, we saw one example in which you can rotate a given shape and see how that appears in after the given rotation. Okay. With this we come to the end of this video. Thank you very much for your attention.